Hello guys, this is Rajvir here and welcome to our new lesson of PLC to VFD Modbus communication as Sky mode. Now this video is for the special request of you enrolled candidates who wants to learn PLC Modbus, so this video is dedicated for you guys. So what we are going to do in this video is we are going to control our VFD using a Modbus communication with a PLC. Alright, so this is the program which we have made for this Modbus communication, and what you can see here is like this is my moderate commands, right? So if you can see in the camera, if I go to K2, this is going to run that drive, and this is the frequency command. Alright, if I put 3500, the motor is going to run at 35 Hertz. 3500 multiple divided by 100 is the number of the hertz which comes out, so it's 35 Hertz. Alright, this is the run command, and I can even change the direction of this motor. For this I have calibrated few constants here. So to change the direction I have to put K34. Now motor is going to stop and it is going to change the direction. Now you can see that direction has been reversed. Alright. So how to make this program, what are the different data registers I have used, what are the bits I have used. I hope you can clear that from this program, right? Just kidding. So let's break up this program and let's see what are the different bits and data registers we have used, how to make this program. Alright, what are the different elements of that. So let me just stop this drive for a moment. Okay, let me just reset the frequency as well. Okay, so let's start with what is Modbus. Modbus is a serial communication between various devices. Now, you know, in the electronic automation world, you may find various types of devices by different manufacturers. Like we have different PLCs, different drives, and different servos, HMI. So if you see the internal, structure of these electronic components, we have memories, we have ICs, we have different registers inside this IC. We have typically that's a memory, right? So this Modbus is directly accessing the memories of different devices. Alright, as you can see here, if you are directly accessing the memories, the ICs or the memory register which are inside the drive, that is a Modbus. Now we are not communicating via some voltage or current, or just like we do in VFD. What we do is we used to convert that 0 to 10 volt into 0 to 50 Hertz, which had converted into frequency. So we use potentiometer to change the frequency. Now suppose if we do not want potentiometer, if you do not want a potentiometer, you want that thing to be done using by directly accessing the memories, that is the Modbus. Right? So how this device will be communicating, this is by several parameters. It says a sky mode, baud rate, parity, data length, and stop bit. This is the different parameter which needs to be similar in both the devices. Right? If baud rate is 9600 in this drive, it should be same in PLC. Parity should be same, data length should be same. So we have to configure the devices by some default parameters. Right? Then only they can communicate with each other. Just like two people can communicate if they know the same language, otherwise it's quite difficult. Similar way, this is the language how they can communicate with each other. So that is a Modbus, right? So this is the wiring diagram of Modbus of a PLC. So PLC is having a port of RS485 at the bottom of that. This is DVP14SS Delta PLC, and this is the inverter port which is generally found here. So if you see in the camera, it is somewhere over here. This is the port. This is the port of Modbus. All right. This is like this. So the same wiring diagram is made in this presentation. This is the Modbus. This is the port which is used in Modbus communication. So here we have third and fourth number pin is negative and positive. So third number is going to the negative of PLC. Fourth number is going to positive of PLC. So that is the wiring. This is the parameter. So now next is how to set these parameters. Okay. So in VFD, now configuring VFD with communication parameters. In VFD, there is a parameter number 92, which says that if you set 01 in 92, it will make this drive at a sky mode. It will do the parity even, data length 7, stop bit 1. So that setting depends on different drives. In some Allen Bradley and Siemens, that will be some different parameters, but that surely exists there. So parameter 92, if we put 01, it will make these parameters. Alright, it will configure the drive with these parameters, with these settings. And for baud rate, it's parameter number 89, you have to put 01 there. Alright, so don't get confused with 01, 89 and 92. That's already written in the manual. You just have to see the manual. That might be 89 or 85 or 82, depends on the drive. Okay, so next is source of frequency command, of course, because we are going to control this drive using 485, that is Modbus. So we have to put 485. That can be, different protocol as well. If you're doing with 485, then you have to use 485. So typically we do Modbus with 485 only. And source of operation command as well 485. That is done by parameter number 00 for frequency, 01 for operation. So that's how that you can put the parameter by putting the values in this parameter on this drive. It's quite easy, quite flexible. You can do it very easily, right? So that's the drive part, how we can put the parameters in the drive. Okay, so next come how to configure PLC with these parameters. That is a tough part, little complex part, but not that tough. Okay, so this is the first ladder which says M1002. Now if you don't know M1002, this is a pulse, this is a bit which gets on when the PLC is at run state, just for a moment. Alright, if you know M1000, which gets on continuously if PLC is running state. This is a bit which gets on just once. It will just give you one pulse when PLC goes from stop to run mode. Okay, so with this single pulse, what it is doing is it is moving H86 in D1120. Now what is that part? So let's discuss this command over here. I'm just breaking the parts. Move H86 D1120. Now first of all, H is a hexadecimal value, 86 is the hexadecimal value. Okay, so if I break this value H86, it will come like this. This is 60110 is the 6, 8 is 1000. That's how you convert hexadecimal into binary, right? First 4 bits representing the 6 and the next 4 bits representing the 8. So it's H86. Now D1120 is a specialized data register inside a PLC which will define its communication parameters. Now that data register is default for this PLC, Delta DVP14SS. It can be different for different PLCs, but it is there. So if you are doing Modbus in this PLC, surely you can do that if you try in others PLC. You just need to understand what are the basics. Basics is we have to configure the devices with same communication parameters. Alright, so now let's see what will happen if I put H86, which is 134 in decimal. Now look at this part, P0, B1, B2, B3. P0 is a bit that defines a data length, and what is the data length we require? That is 7. If you go back here, 7 data length. So we have to put here 0. So bit 0 is 0. Okay, let's come to the next part. Bit 1 and bit 2 is a parity. We need an even parity. This is what is required. Okay, so for even parity, wait, let me just highlight this one. 7 data length, even parity, you have to put 1 1. This is default. These settings are default. This is given in the manual of your devices. Alright, so here we have 1 1. Bit 3, stop bit is 1. 1 bit is stop. Okay, so here we have 0. If you want to check again, 7 data length, parity, even, stop bit 1, SKY mode. Okay, so coming back here, so bit 0, bit 1, bit 2 and bit 3 has been defined. Now let's see the next 4 bits. This 4 bits defines the baud rate. What is the baud rate we require? 9600, that we have put in the drive. So same here, for 9600 you can select that. If you put 0001, it is 110, 150, 600, 4800, 9600 is over here. So this is the baud rate we require. For that we have to put 1000, so it's 1000. Okay, so that's why this becomes H86. So this is the first command. Now if you're suppose communicating this PLC with some other device, maybe the baud rate of other devices is somewhere 1,92,000 or sorry 19,200 or 1,15,200. So you can vary the baud rates. It's up to you, and you can also vary the parity, even data length, stop bits, everything. So this first command, move H86 D1120, has been defined by this H86. Okay, so parameter has been similar now. So let's move next. Next are the 3 commands. This one, M1120, and a further part of this command. It says that set M1120 is again a specialized bit whose function is default. Its function is already default. It says that it is used to hold the communication even if the value in D1120 changed. So what is this D1120? This is the D1120. If suppose the value has been changed by mistake, to avoid some interruption in the program, we can set M1120. It's optional. If you set this one, your communication parameter will not be changed even if the value of this has been changed. Okay, it's a kind of security, security to your communication parameter. So we have to set M1120 in parallel. That will make our program more secure. Now next is the timeout value. Timeout values, by default we have enter 100 milliseconds. Now timeout value is a time for which it will wait for any successful communication. It will wait till the receiver and transmitter have received the data. That is the timeout value. How much time you want your device to wait. So we have took here 100, which is 100 millisecond, 0.1 second. Okay. Now come memory bit 1143, which is again a default bit, which says that if it is on, then your mode is RTU. If it is off, it's ASCII. So our requirement is ASCII mode, so we have to reset that. So our first program, this area of program, this length of program has been defined. We have understood each and everything. Okay. Now let's move beyond. Sending request. Now if you know that in a Modbus we have to send a request to send the data for every device. Our PLC has to get some input that yes, now you have to send the data. We have entered the data, now you have to send that. So we have to send a request there. So for that we have to use this bit M1122. This is again a default bit. Its function is already defined by the manufacturer, that it will send the request to the to the receiver, which is a drive, that I'm sending the data. Okay, when the drive is ready, it will receive the data. So that's how it works. So for that we have to take 3 bits, M0, M1 and M2. Okay, so this M0, M1 and M2 has been turned on by some comparison command of a counter C0. I'll tell you where we are actuating this counter and why we need that, because for every data we have to send the request. So we have to keep sending the request. We have to keep putting this. We have to keep we can see that generate the pulses to this set M1122. So we have also done the reset of counter so that this will continue in a loop. Data sending request is very much required. Suppose if you want your drive to start, you have entered the command of start. Until or unless you actuate this command data sending request, it will not run. Okay, so this needs to be activated every time when your data is entered. If the kind of operation you want to actuate that, you have to keep sending the request. So for that we have to keep generating the pulses here. So how we are generating these pulses, let's see that. So these are the 3 methods however which we are generating the pulses. We are actuating the counter. First is M1129. This is data receiving timeout bit. Okay, now when data has been received, this will be on. So this will again generate a pulse for this data sending request, because if you want to keep sending the data, so this will keep on and off when the data has been received. It's a timeout bit. Okay, then come data received error. So suppose in case your data has not been received, there is an error is there, so that will also that will not halt the program. That will also keep sending the request. It will keep continuing the program. Maybe our second data can be received, our third and fourth data is very important. You want to keep continuing the program, so we have took the loop error also, data received error, to run this counter. Okay, then data receiving completes. So when the data has been received, then again we are actuating a counter. This is the same counter. If you see here, it's C0 everywhere, it's the same counter. So we are actuating the same counter, this C0, by 3 different bits: data receiving timeout, data receive error, data receiving complete. So just to keep continuing the program, I'll show you in the later logic. Then comes your mod write. This is the program which will write the values for different operations of a drive. For example, it's run, jog, forward, reverse, changing the directions. So how does it work? So it says with M1, of course, MODWR, this is a mod write, syntax of mod write command. K1, this is device address, data address. Now this address H2000 is the address of my drive. This is not a PLC address. This is the address of my drive. As I told you that in Modbus we have to directly access the drive. So what PLC is doing is, PLC is writing the value of D10. D10 is the data value. Whatever value will be here, it will be transferred to H2000. Okay. Now it is up to the manufacturer these values, if you see here, K1, K2, 34, this is defined by the manufacturer of my VFD, that if I put K1 into H2000, drive will stop. Okay, this is already defined. If I put K3 into the data address H2000, drive will run in jog mode. If I put K1 stop, K2 run, and if I put K16, it will change the direction to forward. If I put K32, direction will be changed to reverse. Direction will be toggled by 48, and by 18 it will be, direction will also be changed, and also run command will also go there. Okay, so these different values you can put in D10 to change the operation of a drive. That really makes sense. So these value, constant value, we can put in D10, that will be transferred to H2000 immediately at every data setting request. That is a operation control command in Modbus communication. So let's come to the frequency part. This is the frequency part. Here we are also again using mod write frequency control command. Mod write K1, this is a device address. Now this device address means, K1 means this is my first device. So this is my first drive which is connected to my PLC. If I connect another drive, I have to write K2. If all the other parameters are same, I have to write K2. So that will become my next drive. If I have more than 5-6 drives, then I have to write K2, K3, K4, K5. So I can control many drives, maybe I think up to 286 drives, 286 devices can be controlled using Modbus. So that's the the application of Modbus. It's very easy, very flexible. You don't have to put so much of wiring of potentiometer to change the frequency. You can do it using a PLC for fully automatic operations. So that's a device address K1, again data address. Now this 2001 is specified for the frequency of a drive. Okay, as 2000 was for operation, 2001 is for the frequency, and data value D11, this is the value which I'll put from PLC into the memory address of the frequency control register. So it says that if you put K1, that will be equivalent to 0.01 Hertz. If you put K5000, it will be 50 Hertz. Alright, so that's directly proportional. We can put the value, we will get the frequency, and to change the operation, these are the different constants we have. Pretty easy, huh? So then we have how to take a feedback from the drive. If I'm saying it's Modbus, it's two-way communication. You can also read from the drive. For that, the command is mod read, MODRD, that stands for mod read. Now in mod read, I have took M2 bit. Now it says mod read K1 H2120. Now H2120 is my command frequency. I haven't written here, so let me just highlight this one. That is my command frequency, the frequency which I have commanded to my drive. I can write command frequency, and H2103, that is my feedback of output frequency. Output frequency, if you remember, in drive we have output frequency represented by H. So here output frequency is represented by 2103. That is the internal data register which will give you exact feedback of your frequency. Okay, so we can read the values from the drive itself. So all these registers are typically, you don't have to mug it up. It is typically present in the manual of your drive. Okay, this is always there, or you can Google it out. If you don't have it in your manual, you can Google it out. It's always there. Manufacturer always provide you with the data registers of Modbus. Okay, that's the command frequency, that is the output frequency. We can read that, and by default these value will be stored into 1050 and 1051, because we are reading that. We haven't mentioned data register here, but for PLC, if you read the PLC manual, if you are reading 2102, that will automatically be stored into 1050, and 2103 into 1051. That is by default. That's why I have divided this with 100 to get the exact value here. So this was about reading the value, writing the value, understanding the Modbus register. So let's see the exact program now. This is the same program which I just explained you. This is the part of your setting the parameter, move H86. Okay, now if you see here, it will keep on blinking. It is keep on sending the request to the device. Okay, that is data receiving complete feedback. The bits are getting on and off. You cannot see that, but it's actually getting on and off because they are also resetting itself. by this how counter is running. This is the equivalent bit by which we are turning on M0, M1, M2 in a continuous loop. This pulses are given to set 1122 here. Okay. Now coming to the mod write. This is the mod write M0. So here it is K1. K1 says motor stop. Let me put K2. Okay, before that let me put some frequency so that I can see the motor running. So here right now it's K0, frequency is 0. I'm putting K3500. We'll find frequency 3500. Hold on. Then here you can see 3500. That is a commanded frequency. Now let me put here K2. Now you can find the drive is running. You can also see the motor, it's running. Okay. K2 is for run. Now if I put K3, that will make jog run. Jog is by default 6 Hz, I guess. Okay, before that I think I have to stop the motor. K1. Then I'll put K3. Now you can see that motor is at jog mode. It is having a 6 frequency and motor is running over here as well. Okay, so let's stop the jog. Now let's try this forward plus run K18. Okay, the motor is running at forward. Okay, to make it reverse we have to put 34. Now there is some deceleration time, so it's taking time to stop and getting reverse. So now it's rotating at reverse direction. Okay, so if I put 48, it will just toggle the direction. So it will do the similar operation. Okay, now as I have given both the commands, so I have to first stop the motor. Now right now my drive is at forward mode. It's written over here, it's forward. So to toggle the direction I put 48. Now it will keep on toggling because, let me just wait. Now you can see that it's now at reverse. Okay. Actually what happens if you're going to toggle the direction, you just have to give the toggle command by just sending a pulse. You don't have to continuously send 48, so that will create a problem. So if I put 48 here, what will happen here, you will see it's toggling forward reverse forward reverse forward reverse. Why it's happening? Because at every moment this 48 is going. So when it goes to forward, pulse comes, it goes to reverse, pulse comes, it will go to forward. So you just have to change the toggle direction just once. Okay, so let's just avoid this right now. Now I'm putting 18, that is forward and run. Okay, so you can even change the frequency here. Okay, 2000, 20 Hertz, 200, 2 Hertz. So similarly, if I put 5000, it will take it to 50 Hertz. And here you can see that this is the commanded frequency, this is the feedback frequency, which is being reflected by this H. Okay, so if you see here D1, that is the exact replication of this H here, H50. So let me just change the frequency. You can see that both getting changed proportionally. I'm putting here K100, 1 Hertz. Can you see here it is decreasing, and similar way it is decreasing in the drive itself. Now it's going at 1 Hertz. Okay, which I guess drive will not take 1 Hertz. I have to put some more value. Wait. So minimum value drive requires a minimum value to run at 1 Hertz is not valid. So that was about Modbus communication. So our main resistors are 2000, 2001 to give the value, and even you can give the value using an HMI, connect an HMI, take some pneumatic interrupt D10, D11, or you can take some buttons and you can move the value. So it will make very easy to control the drive using an HMI just by 2 wires RS485. That is the beauty of this Modbus communication. Similar way you can control your PIDs, and you can also control this drive directly from HMI without the use of PLC, again by Modbus. Okay, that will be doing in later on lessons. So that was all about PLC to VFD Modbus communication as SCHI mode between Delta 14SS and Delta VFD M series. So if you have any queries, any doubt, you can post a comment in this video or you can write me a mail. Thank you so much.